Hello everybody, Eric again. Like and subscribe. Here we go. Let's read about the faster, better, cheaper approach. The faster, better, cheaper approach, FBC, was a management philosophy adopted by NASA under Administrator Daniel Goldin, 1992 to 2001, following the end of the Cold War and facing budget constraints. NASA sought to reduce mission costs and development time while maintaining scientific capabilities through smaller, more focused missions and increased use of commercial technologies. History. NASA had a difficult period in the 1990s with the Cold War and the space race between the US and the USSR finished. The agency saw dwindling budgets, and the new NASA administrator, Daniel Goldin, introduced the so-called faster, better, cheaper approach in 1992, which encouraged smaller, cheaper missions built with the help of third-party contractors, efficiently commercializing the research labs and forcing them to work with industry. Goldin had experience with small satellites and especially disliked long, expensive programs, calling them Battlestar Galacticas, like the Cassini mission that he threatened to cancel, and urged for development of small and fast missions. The FBC approach was compared and likely originated from Lockheed Martin's Skunk Works approach developed by Kelly Johnson, though it was promoted by NASA and was a de facto operational program during Goldin's tenure. FBC was not institutionalized into NASA policies, being only a set of unwritten ideas. The faster, better, cheaper approach was described as fast replies to project development time, which for convenience can be defined as the period from project approval to launch. Rapid development cycles help control costs and enable the incorporation of the latest advances in technology, because the design freeze date is closest to the launch date, better applies to the capability of the flight system as a scientific instrument. Improvement here is based on the use of advanced technologies and on better focused science based on the knowledge gained from earlier exploration missions. Finally, cheaper donates both lower costs per mission and through clever design and use of technology, more effective use of available funds. In 1991, Edward C. Stone, a well-known enthusiast and respectable scientist, the project scientist of Voyager program, was made the Jet Propulsion Laboratory JPL director. JPL had little experience in small missions at the time. Its flagship missions, like Voyager, Cassini, and Galileo, employed hundreds of people for decades. Cassini, for example, directly supported maybe 500 work years, about 10% of total lab staff, and provided close to 20% of the lab budget. In order to comply with budget restrictions and save the mission, Cassini was downsized to save $250 million. The SCAN platform had to be removed from the plans. Stone himself saw the faster, better, cheaper as a cultural change of the lab's engineering practices. The most successful model example of the FBC was the Mars Pathfinder lander and the first Mars rover, the Sojourner. The mission cost around $200 million and was widely reported in the press, appearing on the covers of Time and Newsweek. FBC also promoted the usage of commercial off-the-shelf hardware and software in spacecraft, for example using commercial CPUs instead of socialized radiation-hardened ones, usually used in spacecraft. The approach was successfully used for the Sojourner. Other missions were less fortunate. In 1998 to 1999, 6 missions were launched. 4 of them failed. Both JPL, Stone, and the NASA administration, Goldin, acknowledged that they pushed it too far. With the FBC, no project manager of the failed missions was fired. Goldin took on the blame, speaking at a press conference at JPL after 2 Mars mission failures. I asked these people to do incredibly tough things to push the limits. we were successful, and I asked them to push harder, and we hit the boundary, and told them they should not apologize. They did terrific things, and I pushed it too hard, and that's why I feel responsible. After Mars Climate Orbiter, Mars Polar Lander, and Deep Space Two failures, a governmental commission, the Mars Program Independent Assessment Team, was created to investigate the issues that led to it. The commission issued the Mars Program Independent Assessment Team report, commonly known as the Young Report, after its chairman, Tom Young. After 2 Mars spacecraft failed, the Mars program had retrenched and returned to more conservative and traditional management, with significantly more funding. The next mission, Mars Exploration Rover, launched in 2003, was redesigned and eventually cost around $800 million. As Norman Haynes put it, MER sucked up all available money from NASA and JPL. The Goddard Space Flight Center operated the Small Explorer Project, SMEX, under the FBC. In 2001, 5 satellites were operational, with just 1 instrument anomaly. Because of the FBC, NASA's Spitzer Space Telescope was forced to change, resulting in simplified instruments, solar orbit, and warm launch architecture. Assessment and legacy. The faster, better, cheaper philosophy is often criticized, with many opponents saying that one can only pick 2 out of 3 desired quantities. However, even its critics encourage that under Golden, the flight rate became higher, and that Golden rescued space science from the tedium and inherent risk of flying one giant mission every 5 or 10 years. The FBC philosophy was noted by multiple authors to be assessed by different criteria. The FBC missions have strict budgets. Mars Pathfinder, together with the Sojourner rover, cost only 6.7% of what was spent on the Viking mission. All 16 missions launched in the FBC era cost less than Cassini. Dan Wood from the U.S. Air Force concludes that FBC delivered 10 successful missions, plus 6 unsuccessful ones, for less than the price of one traditional mission, suggests that success per dollar is more meaningful measurement of achievement than success per attempt, because there is no limit to the number of attempts we can make, and writes that FBC reveals an honorable record of success. Another metric which shows that FBC was a successful approach is the science outputs per dollar of mission costs. FBC missions resulted in more scientific publications and citation-weighted publications per dollar of mission costs than did missions developed under other paradigms. Dillon and Madsen 2014 concludes that NASA suffers from bias against learning from the FBC era because of the stigma of the failed projects. Jalabidi F. Magnami wrote that the popular belief is one to target the FBC approach, and shows that the percentage of failed missions was not much lower before FBC than during the FBC. Larry J. Paxton thought the FBC did revolutionize science at NASA. During the Golden administration, there were many missions, in contrast with the flagship Voyager and Galileo. New NASA programs were created, including the Discovery Program and Living with a Star. He also wrote that FBC proves that large organizations like NASA can be changed and adapted to the needs of its customers. For NASA, that customer base included politicians, scientists, and the public. Howard E. McCurdy wrote that history may view Golden's administration as a bold first step towards displacing an inappropriate and unsustainable culture of uncontrolled spending on space. Daniel Golden was NASA administrator under 3 presidents, from 1992 to 2001, the youngest tenure of all NASA directors. According to W. Henry Lambright, he was hailed at one point as a miracle worker and posted for a government reinvention for his faster, better, cheaper strategy of doing more than with less. But Golden left the agency under fire for cost overruns and reforms that reached too far. Influence on other agencies. Through ESA, never adopted NASA's FBC. The agency was also looking into low-cost missions in the early 2000s. The first European planetary mission, the Mars Express Orbiter, and the Beagle 2 lander cost only $60 million and had a streamlined design and threat which echoes a previous NASA mantra, faster, better, cheaper. ESA described it as the first example of ESA's new style of developing scientific missions, faster, smarter, and more cost-effective, but without compromising reliability and quality. ESA stated that there was immense pressure on ESA from its member states to demonstrate similar principles on from its member states to demonstrate similar principles to FBC. ESA Science Director David Southward adapted the FBC as faster, smarter, cheaper. The orbiter missions succeeded, but the lander failed. European smallsats, PROBA, PRO-BA, were designed according to the FBC principles. The first satellite, PRO-BA-1, was launched in 2001. In 1997, ESA proposed to radically restructure the Horizon 2000 program to make missions faster and cheaper. Takahiro Yamada of JAXA wrote positively of the FBC approach. Far faster, far better, far cheaper may be difficult, but a little faster, a little better, a little cheaper must be within the scope of our endeavors. Missions. Sources usually mention 16 missions launched during the FBC era, though several more missions are also attributed to it by others. Mission name, program, operator, launch date, budget million USD, operation period, outcome, notes, refs, Clementine, DSPSE, BMDO/NRL, the 25th of January, 1994, $75. $75 million. $75 million. 1994. Success. Completed global lunar mapping. Planned flyby of 1620. Geogropus canceled after attitude failure. Mission became the basis of FBC. SAM. PX. SM. EX. GSFC. July 3rd, 1992. $55 million. 1992 to 2004. Success. First SMEX mission. Study cosmic waves and magnetospheric particles. NEAR. Shoemaker. Discovery. APL/JHU. February 17, 1996. $110 to $150 million. 1996 to 2001. Success. First spacecraft to orbit and land on an asteroid. Mars Pathfinder and the Sojourner rover. Discovery. JPL. December 4, 1996. $280 million. 1996 to 1997. Success. First Mars rover. 85 days operation. Mars Global Surveyor. Mars Surveyor. JPL. November 7, 1996. $154 million. 1996 to 2006. Success. 9+ years of Mars mapping. 240,000 plus images. Fast. SMEX. GSFC. August 21st, 1996. $35 million. 1996 to 2009. Success. Aurora Research. Exceeded Design Life. Lewis Small Satellite Technology Initiative. NASA Glenn/TWR. TRW. August 23rd, 1997. $62 million. Failed 3 days post-launch. Failure. Attitude control system failure. Clark Small Satellite Technology Initiative. NASA Stennis. Planned 1997. $60 million. Canceled February 1998. Canceled SSTI program termination. Lunar Prospector, Discovery, NASA Ames, January 6, 1998, $62.8 million, 1998 to 1999, success, found evidence of lunar water ice, Deep Space One, New Millennium, JPL, October 24, 1998, $150 million, 1998 to 2001, success, technology demonstration, Eon propulsion, Mars Climate Orbiter, Mars Surveyor, JPL, December 11th, 1998, $125 million, 1998 to 1999, failure, lost to metric/imperial units error, SWAS, SMEX, JN, GSFC, December 5th, 1998, $70 million, 1998 to 2008, success, sub-millimeter astronomy observations, trace, SMEX, GSFC, April 1st, 1998, $75 million, 1998 to 2010, success, solar corona imaging and research, Stardust, Discovery, JPL, Lockheed Martin, February 7th, 1999, $200 million, 1999 to 2011, success, first comet sample return mission, Deep Space Two, New Millennium, JPL, January 3rd, 1999, $28 million, 1999, failure, lost with Mars Polar Lander, Mars Polar Lander, Mars Surveyor, JPL, January 3rd, 1999, $165 million, 1999, failure, lost during landing attempt, Wire, SMEX, GSFC, March 4th, 1999, $80 million, 1999, failure, premature ejection of telescope cover, Terriers, Explorers Program, Boston University, May 18, 1999, $6.1 million, failed after launch, failure, LE2 control system failure, lost power, Genesis, Discovery, JPL/Lockheed Martin, the 8th of August, 2001, $264 million, 2001 to 2004, partial success, collected solar wind samples, return capsule parachute failed, samples still largely recovered. Contour, Discovery, APL/JHU, the 3rd of July, 2002, $159 million, 2002, failure, lost contact after solid rocket, motor burned, spacecraft presumed destroyed. Further reading, Pat Cornell, E. Dillon R., 1998, Challenges in the Management of Faster, Better, Cheaper Space Missions, 1998, IEEE, Aerospace Conference, Proceedings, CAT, number 98TH8339, Volume 5, Showmass, Colorado, USA, pages 507 to 514, Doe, 10.1109/Euro, 1998, .685861. Schapper Lisa R., 1998, International Coordination in the Era of Faster, Better, Cheaper, Space Policy, 14, 2, 89-94, Bibcode, Code, 1998, SPPLL, 14, 89S. Bye for now.